Welcome all. Last time we looked into the analysis methods, we looked into the response of a system subjected to triangular loading, we looked into the response of the system subjected to the pulse loading, half sine loading. Okay. After that we looked into how to analyze the system using single degree of freedom approximation, and after that we also looked into the use of the design charts for evaluating the maximum response. We also looked into the use of equivalent static force method in order to calculate the maximum bending moment, shear forces and other quantities of interest. So, today we will be extending the things and we will be looking into the design aspects also. So, today's content will cover the design of the structural steel elements and the design of the reinforced concrete elements subjected to blast loading. Okay. So, what is the difference between the steel and the concrete structures when it comes down to the protective design? Protective design means that we are designing the structure to withstand the impact and blast type of loadings. Okay. So, hallmark of steel structure. Steel structure have high ductility, okay. They have high ductility and they have strain rate sensitivity. Okay. And due to all these quantities, okay, already we have seen that the area under the stress strain curve for the steel is large. Okay. So, since this area is large, it means that it can absorb large dynamic blast loading. Okay. Steel elements can undergo large plastic deformation. Okay. The deformation, the total deformation undergone by the steel element is large. Okay. So, it is undergoing large plastic deformations and the brittle failure is not occurring in steel structure. Okay. So, it makes the steel elements a favorable element for the blast resistance. Normally in steel structures, the failure is usually due to buckling or excessive deformation rather than sudden collapse. Okay. So, there will be always a warning sign whenever a steel structure is about to collapse. Okay. And the warning signs will be visible, it will not be a sudden collapse. Okay. So, due to its high energy absorbing nature, large plastic deformations and significant warnings before any type of collapse occurs, steel becomes a favorable material for the design of blast loading. Okay. So, it becomes a material of choice. Okay. Now, let us look into the concrete structures. Concrete structures have high compressive strength, but they have low tensile strength and ductility. Okay. Invariably, if we are comparing a reinforced concrete structure and a steel structure, there are high chances that the steel structure has more ductility than the concrete structures. Okay. In addition to that, the concrete structures are vulnerable to spalling, okay, cracking and fragmentation under the blast loading. Okay. As we have seen, if a blast loading or an impact type of loading occurs, okay, there will be spalling in the concrete, okay, cracks will be forming, okay, and it will try to fragment out. Okay. So, these are the inherent drawbacks of a concrete type of structure. Okay. Reinforcement, okay, that is nothing but a steel rebar, is crucial to improve ductility and the tensile resistance. Okay. So, as we have told earlier, the concrete is bad in resisting the tensile loads. Okay. So, we normally supplement it or reinforce it using the steel rebars, okay, to improve its ductility and the tensile resistance. Normally, the failure in the concrete structures is often due to the brittle and localized manner as compared to the steel structures. Okay. So, even if we are designing, okay, using steel rebars as reinforcement, okay, that is trying to improve the ductility and the tensile resistance, but due to this high impact nature of the blast and impact loading, the brittle and the failure in a localized manner is occurring more often in the concrete structures. So, now we are looking into the design of steel structural elements. So, different types of elements are being broken down depending upon their usage and what things they are going to give. Okay. So, there are something known as the accepted type of structures. Okay. So, what is an accepted type of structure? The accepted type of structures are removed from the immediate vicinity of the detonation. Okay. They include typical frame structures with beam columns composed of standard structural shape and built up sections. Okay. The relatively low blast pressure suggests the use of standard building components such as open wave joists, prefabricated wall panels and roof decking detailed as required to carry the full magnitude of the dynamic loading. Okay. So, these are the acceptor type of structures. Okay. Another application of the acceptor type of structure can be the use of entire pre-engineered buildings, okay, strengthened locally to adapt this design to low blast pressure. Okay. So, they are typically used for a low blast scenario. Okay. For example, certain type of hangar structures, okay, where the structural element itself can only withstand low intensity blast pressure, but then it is removed from outside, okay, using soil conditions or pre-hardened structural elements to such that the entire system can take more amount of loading. Okay. So, the entire base structure, okay, the middle structure is a structure acceptor type of structure which can only withstand low blast pressure, but the exterior elements are reinforced, okay, using soil or other hardened materials so that it can take more intensity of blast loading. Okay. So, there are other type of structures called the donor type of structures. Okay. So, they are located in the immediate vicinity of the detonation. Okay. The acceptor type of structures are not located in the immediate vicinity of the detonation, and hence the blast carrying capacity of these structures is low. The donor type of structure, they are located in the immediate vicinity of the detonation. Okay. And they are normally made of steel containment cell or steel components of reinforced concrete containment structures such as blast doors or ventilation and the electrical closure panel. It means that they are hardened type of structures. Okay. In some cases, the use of suppressive shielding to control or confine the hazardous blast, fragment and flame effects of the detonation may be an economically feasible alternative. Okay. So, they are also shielded, okay, to control the effects of the blast or the fragment things. Okay. The blast pressure encountered here is of high magnitude, okay, and this suggests the use of large plates or built up sections with relatively high resistance. Okay. It means that this donor type of structures are hardened structures, okay, and they are reinforced with built up sections or relatively high resistance sections, so that the high intensity of the blast loading can be negated. Okay. And in some instances, fragment impact or pressure leakage is permitted. Okay. So, depending upon the usage of the structure, this type of things, the fragmentation impact or pressure leakage might or might not be permitted. Okay. So, basically the acceptor type of structure, they are used to resist the low type of blast loading. The donor type of structure, they are made to resist the high intensity of blast loading. Dynamic design. Okay. How to design this system? Okay. The first step in dynamic design entails the development of a trial design considering facility requirements, available materials and economy, with members sized by a simple preliminary procedure. Okay. So, a first trial is required, okay, depending upon the requirement of the facility, the uses of the facility, okay, the available materials and the economy that can be achieved by the existing materials. Okay. So, a trial design method is first applied to get the initial configuration. Okay. After we have the initial configuration, the second step involves the performance of a dynamic analysis. Okay. After the initial configuration, dynamic analysis is performed on the system to determine the response of the trial design to the blast compared to the maximum allowable response. Okay. It means that first of all, depending upon the requirement, okay, an initial configuration is first made. Okay. So, this is the initial configuration depending upon the availability of the material, the usage and other factors, and this is the first step. Okay. In the second step, this entire thing, okay, is subjected to a dynamic analysis. Okay. The blast loading is applied using the approximations, okay, and the responses are calculated. Okay. U naught max, okay, bending moment, shear force, okay, and then they are compared with the U standard, okay, the value of the allowable deflection, okay, the value of the allowable stresses. Okay. So, this responses are compared with the deformation limits specified. Okay. The actual deformations are then compared with the limits specified. Okay. And in the final design, it is then determined by achieving an economical balance between the stiffness and the resistance, such that the calculated response under the blast loading lies within the limited value. dictated by the operational requirement of the facility. Okay. So, once we have this comparison, okay, now this thing is being optimized, okay, to achieve a parity between the economy as well as the requirement of the resistance. Okay. So, these are the 3 design steps. Okay. Initial design, okay, preliminary arrangement of the elements, then the analysis, okay, to check whether they are under deflection limits or not, and once this is checked, then this design is optimized to obtain a parity between the economy and the resistance of the system. Okay. And then the most economical design within the due limits of the resistance is been adopted. Okay. So, this is in this way a 3-step design procedure is being followed. So, the mechanical properties of structural steel. Okay. Under the dynamic loading, the application of the loading is rapid. Okay. So, here the strain rate comes into play. Okay. So, we have discussed about the strain rates. So, we have seen that the stress strain curve, okay, the stress strain curve depends upon the rate of loading. Okay. So, as the rate of loading is increased, okay, the value of the maximum stress also increases. Okay. Though sometimes there is a loss in the strain, okay, but the stresses are increased. Okay. So, this is an estimate of the strain rate. Okay. So, strain rate. So, this is the average strain rate in the elastic range of the steel. T is the time to yield and FDS is the dynamic design stress. Okay. So, as compared to the static stress, okay, there is an increase in the dynamic range. Okay. So, due to the strain rate, okay, this dynamic effect comes into play, okay, which can be used in the design purpose. Okay. The yield point increases substantially to the dynamic yield stress value. Okay. This effect is termed as that dynamic increase factor for the yield stresses. Okay. It simply means that the ratio of the dynamic stresses to the Fy is becoming large, okay, as the value of the strain rate is increasing. Okay. Modulus more or less remains unchanged. It means that the slope of this curve, okay, more or less it remains constant. Okay. There is a slight increase in the ultimate tensile strength. Okay. The increase in the ultimate tensile strength, okay, there is a slight increase. Okay. This effect is termed as the dynamic increase factor for the ultimate stresses. Okay. Elongation at rupture, okay, it means that this value. Okay. So, this value at rupture, okay, is normally unchanged or there might be a slight reduction, okay, in this particular value. Okay. So, this is the behavior of the steel, okay, under the influence of the increasing rate of loading. So, these are some of the values that are given in the design books which are normally used in the design purpose. Okay. So, here we are looking for different types of material. A36 simply means that the yield stress of this particular steel is 36 KSI. Okay. Again, these are the different nomenclature of the steel, okay, where this symbol denotes normally the yield stress of the steel. Okay. So, the behavior of these components, okay, under different loading conditions. Okay. So, this is the behavior under bending and this is the behavior under tension or compression. Okay. So, under the low strain rate and under the high strain rate, okay, there is then increase in the value of the yield stress. Okay. So, for A36 steel the increase is approximately 30%, here 20% and here approximately 10%. Okay. During high pressure region, if it is under the high pressure region, this increase is as high as 36%. Okay. This is as high as 36%. Again, under tension or compression type of loading, okay, this is the estimate of the increase in the yield stress of the structural steel. Okay. So, steel protective structures and members are generally not designed for excessive deflections. Okay. So, the deflection is limited, okay, in case of the protective structures. Okay. Some situation arise where the excessive deflections may be tolerated and will not lead to a structural failure or collapse. Okay. So, this depends upon the functionality of the structure. Okay. The protective structure, it is designed for which purpose, okay, that might or might not allow the excessive deflection. So, in this case where the excessive deflection might be allowed, the ultimate stresses and the associated dynamic increase factor must be considered. Okay. It means that when we are allowing the excessive deflections, okay, then the increase in the ultimate stresses might be considered. Okay. So, these are the factor for increase in the ultimate stresses. Okay. So, this was the factor for the yield stress. Okay. This is the factor increase for the ultimate stress. Okay. So, again we can see that this factor is not more. Okay. Maximum increase allowed is maybe 10%, okay, for the 836 type of steel. Okay. So, these are the allowable increase in the stresses for the different scenarios depending upon the steel, different grades of steel that are being used. So, here also a similar thing is shown. So, this is the dynamic increase factor for the yield stresses at various strain rates for these two grades of steel, okay, A36 grade of steel and A514 grade of steel. Okay. So, this is the dynamic increase factor. So, there we were showing the numbers. So, here there is a continuous curve, okay, depending upon the strain rate. So, as you can see, if we keep on increasing the strain rate, okay, there is a significant increase in the value of the yield stresses. Okay. So, for A36 type of steel, we can see that it can increase as high as 1.7. Okay. It means that there is a increase in 70%. Okay. And for the other grade of steel, okay, it increases to at least about 20%. Okay. And depending upon the thickness of the material, okay, then it attains a constant quantity. Okay. So, we are looking into the mechanical properties of the structural steel. Okay. So, these are the recommended dynamic design stresses. Okay. So, when we are using the steel for the design purposes, these are the recommended value. Okay. So, if we are looking into a ductility ratio, okay, of less than 10, okay, it means that U plastic divided by U elastic, okay, or strain plastic divided by strain elastic, okay, if it is less than 10, okay, then this equation can be used to calculate the increase in the dynamic design stresses. Okay. So, FDY is the dynamic yield stress, C is the dynamic increase factor or the yield stress factor, A is the average strength increase factor. So, this is used 1.1 for steel with a specified minimum yield stress of 50 KSI or less, okay, or 1 otherwise. Okay. So, if the yield stresses is 50 KSI or less, 1 is used, 1.1 is used. If it is more than that, then 1 is being used. And Fy is the static yield stresses. Okay. So, for A36 type of steel, this is just 36 KSI. Okay. If the ductility ratio is more, okay, if the ductility ratio is more, an equation, okay, accounting for this increased ductility is used. Okay. So, here an additional factor comes into picture which accounts for the increased ductility ratio. Okay. And table 5.1, table 5.3 or figure 5.2 can be used to calculate the entire quantity. Okay. For bending, okay, so for the design stresses for bending, okay, there is a significant increases allowed. Okay. But for the dynamic shear, so in case of shear which is highly unpredictable, okay, the increase is a bit restricted. Okay. So, whatever we are calculating for the dynamic design stresses, okay, 0.55 times of this will be used for the dynamic shear stresses. Okay. So, deformation criteria, we are looking into the different deformation criteria. So, ductility ratio, okay, if we are considering the ductility ratio in terms of the maximum deflection divided by the elastic deflection, okay, if this formulation is being used for the determining the ductility ratio. So, for beam, maximum rotation up to 12 degree or maximum ductility ratio of 20 is being allowed. Okay. It means that 20 times the maximum elastic deflection is allowed, okay, when we are designing the beams to sustain a blast loading. Okay. And for personnel or equipment safety, okay, this limit of rotation is restricted to 2 degree and the ductility has been restricted to less than 10. Okay. So, theta allowed here was 12 degree and ductility ratio, okay, if you are expressing this thing in terms of xm divided by xc, okay, a ratio of the maximum deflection and the elastic deflection. So normally it is 20, okay, and for the personal equipment safety, this has been toned down to 2 degrees, okay. From 12 degree it has been toned down to 2 degrees, and from 20 degrees it has been toned down to less than 10, okay. If you are using the frame structural criteria, okay, so sideway deflection should be less than 1/25th of the story height, okay. So this sideway deflection delta, okay, should be less than 1/25th of the story height, okay. So this is the criteria for the beam sway, okay, and maximum member rotation, okay, that has been restricted to 2 degrees, okay. So in case of the framing criteria, plate deformation criteria and modes, okay. So plate might be allowed for large support rotation up to 12 degree and ductility ratio up to 20, okay. So plate are allowed with much larger rotational criteria and the ductility ratio, okay. This things, okay, has to be restricted if the plates needs to be used, okay, reused, okay. If the reusability criteria comes into picture, then this criteria are tightened more, okay, and they should have high values for incipient failure and the high energy absorption, okay. So depending upon the criteria set, okay, depending upon the usage, different criteria are set for the different structural system. In any given structures, there are secondary modes of failure. So that also needs to be accounted when the design process is being targeted, okay. So the overall buckling, okay, the overall buckling depends upon the symmetry and the loading condition, okay. So there will be an overall buckling in the system, there will be a local buckling, okay, that is the flange buckling, web buckling. So all this criteria needs to be fulfilled, okay, whenever a system is being designed, okay. So normally AISC provisions for frame up to 2 stories is being followed, okay, and there should be bracings for taller frames, okay, or if some requirement is needed as per the dynamic analysis, okay. So buckling criteria needs to be checked, okay, overall buckling criteria, local buckling criteria of the flange and of the waves needs to be checked, and up till 2 stories of frame, okay, AISC provisions are required to be fulfilled, and for the taller structures, okay, bracings are must, okay, as per the need of the dynamic analysis dictates, okay. Brittle failures. So the brittle failures are highly sensitive to the residual stretches, okay, they occur due to poor welding, there is a notching in the steel, okay, due to the shock loading, low temperature and the strain aging, okay. So this all the brittle failure modes, okay, coming from the different causes, okay, poor welding, residual stresses, there is a notch in the steel element present, there is a localized shock effect, okay, the steel is subjected to low strains, okay, there is a strain aging, okay. So all these things might occur, okay. So there is a need for prevention, so we need to choose the appropriate material, okay, so that this brittle type of failure modes are avoided, okay. It needs a careful fabrication, workmanship and fabrication, okay. These are the key for a steel structure, okay. So the workmanship and fabrication should be controlled to a greater extent, and the connections, all the connections should be designed for ensuring ductility, okay. Let us say we are designing a frame type of system, okay. We have designed the beam properly, we have designed the column properly, okay, but we have ignored the increase in the stresses, okay, that are coming at the connections, okay. So if we do not design, if we do not take into account all these factors, what will happen is that my beam might survive, my column might survive, okay, but there will be a severe distortion in the connection, okay, and the overall requirement, okay, for which this entire framing system was designed will be defeated, okay. Though we have put the best material, we have used the best design purposes, but we have ignored the design consideration in the connections, okay. So our entire purpose will be defeated, okay. So the requirement for a proper connection design is a must in case of blast and impact loading, okay. So beam design under blast loading, okay. So the ultimate dynamic moment resistance, okay, has been given by the increase in the stresses due to the strain rate effect times the sectional capacity, okay. So FDS is the dynamic design stress derived from the blast specific factors, and Z is the plastic section modulus. Okay. So, this is nothing but the sum of the fully yielded cross section area relative to the neutral axis. Okay. So, in the elastic design, what we were used to calculate the section modulus depending upon the system remains in the elastic state. Okay. So, here we will use a design modulus where my entire section is in the plastic range. Okay. So, this is called the plastic section modulus, and the earlier one the S that we were used to, this was the elastic section modulus. Okay. The calculation of the plastic section modulus. Okay. For a doubly symmetrical sections, okay, the section modulus is been given by the relative area in compression and tension, AC in compression and AT in tension. Okay, AT in tension. M1, M2 are distance from the neutral axis to the centroidal of the compression and the tension area. Okay. For a standard I type of section, as W and M type of section, the plastic section modulus is approximately 1.15 times the elastic modulus for strong axis bending, and may be obtained from the standard manuals or the structural steel design. Okay. So, in the steel table, normally the elastic section modulus and plastic section modulus both are given. If only elastic section modulus is given, so for the standard sections, standard I type of sections, we can multiply by 1.15 times the elastic modulus in order to obtain my plastic section modulus. Okay. So, this is a conservative way to obtain the design properties. Okay. So, in this way one by one we can look it into the properties and design my sections. Okay. So, today we will stop here, and next time onwards we will look into the specific examples of design of the steel sections. Thank you.